Pluto's atmosphere is 30 degrees colder than physics says it should be, and for 8 years nobody could explain why. Then, in June 2025, the James Webb Space Telescope caught the culprit red-handed, confirming an idea most planetary scientists once dismissed as impossible. This is a real peer-reviewed discovery, and it might be one of the strangest climate systems ever found in our solar system. Let's rewind to July 2015, when NASA's New Horizons spacecraft became the first and only mission ever to fly directly past Pluto. Scientists expected a dead, unremarkable little world. Instead, they found towering mountains built from water ice, smooth plains of frozen nitrogen stretching for hundreds of miles, and hanging above all of it, something nobody had anticipated, a thin, delicate haze, wrapping the entire planet in layered blue. That haze wasn't dense, but it extended nearly 200 miles above the surface, far higher than anyone expected a small, distant world like Pluto could sustain. It's worth appreciating just how remarkable it was that scientists had any close-up data on Pluto at all by that point. Pluto was discovered back in 1930 by American astronomer Clyde Tombaugh, working at Lowell Observatory in Arizona, after a painstaking search for a predicted planet thought to be influencing the orbits of Neptune and Uranus. For decades afterward, Pluto remained little more than a faint, blurry point of light, even through the most powerful telescopes available, simply too small and too distant to resolve any real surface detail. New Horizons launched in January 2006, specifically to finally get a close look, and it took more than 9 years of travel, covering roughly 3 billion miles, before it finally reached its target. Because Pluto is so far from the Sun, New Horizons couldn't simply slow down and enter orbit the way missions to closer planets often do. Instead, it performed a single fast flyby, gathering as much data as possible during a brief window of close approach before continuing onward into the distant Kuiper Belt. That flyby remains, to this day, humanity's only close-up visit to Pluto, and everything learned since, including this haze discovery, has come from analyzing that data set alongside remote observations from telescopes back here in our own solar system. The real puzzle wasn't the haze's beauty, though. It was Pluto's temperature. Based on standard atmospheric models, factoring in how much sunlight actually reaches a world this far from the Sun, and how nitrogen and methane gases typically behave, Pluto's atmosphere should have settled at a specific, predictable temperature. The real measurements came in dramatically colder. Instead, roughly 30 degrees Celsius below what the models predicted. That's not a rounding error. That's the kind of gap that tells you your underlying model is missing something fundamental. For years afterward, researchers reran the calculations, recalibrated their instruments, and rechecked the New Horizons data from every possible angle. And the numbers simply refused to add up. Something was pulling extra heat out of Pluto's thin atmosphere, and nobody could identify what it was. In 2017, a planetary scientist named Xi Zhang at the University of California, Santa Cruz, proposed an idea that struck many of his colleagues as genuinely far-fetched. What if Pluto's haze wasn't just a passive decorative layer sitting quietly in the atmosphere? What if those microscopic solid particles were actively controlling the planet's entire energy balance? Zhang's theory suggested the haze could absorb incoming sunlight and then re-emit that energy, not as visible light, but specifically as mid-infrared radiation, heat escaping directly out into space. If that were true, the haze wouldn't just reflect a little sunlight the way scientists assumed. It would function almost like an active thermal radiator, bleeding heat away from the planet far more efficiently than ordinary atmospheric gases ever could, and that extra heat loss could fully explain Pluto's mysteriously cold atmosphere. Plenty of scientists were skeptical at the time. The idea that solid particles rather than gases could dominate a planet's temperature control cut directly against a lot of standard planetary science thinking. But Zhang's theory came with a specific, testable prediction attached. If his idea was correct, Pluto's haze should be glowing faintly in a very particular range of mid-infrared wavelengths, a signal so faint that only one instrument in existence would ever be sensitive enough to detect it, the mid-infrared. Instrument, or MIRI, aboard the James Webb Space Telescope, which, in 2017, hadn't even launched yet. That opportunity finally arrived in 2022, once Webb reached its observing position and began science operations. In 2023, an international research team led by astronomer Tanguy Bertrand at the Paris Observatory pointed Webb's instruments directly at Pluto and its large moon Charon. This mattered enormously because Charon orbits so close to Pluto that earlier telescopes, including Spitzer and the European Space Agency's Herschel Observatory, had already detected faint mid-infrared emissions coming from the Pluto system as far back as 1997. But none of them had the resolution needed to tell which world the signal was actually coming from. Webb, with its considerably larger mirror and far more sensitive instruments, finally had the precision to separate the two signals for the first time in history. If watching a genuinely bold scientific prediction, sit unconfirmed for the better part of a decade before finally getting proven right is exactly the kind of story you come here for. Go ahead and subscribe, because we track discoveries like this one as they happen. Using MIRI, the team scanned across multiple infrared wavelengths, and the results were striking. Pluto's infrared glow was noticeably stronger than its frozen surface alone could explain. Once researchers subtracted Charon's separate contribution from the combined signal, isolating Pluto's atmosphere specifically, the remaining data matched Zhang's 2017 prediction closely. The haze wasn't simply scattering incoming sunlight around, it was actively glowing in mid-infrared wavelengths, radiating heat outward exactly the way his theory had predicted 6 years earlier. Zhang himself later said, "It isn't common in planetary science for a hypothesis to be confirmed this cleanly within less than a decade of first proposing it, and that the team felt genuinely fortunate to see it happen." The research, led by Bertrand along with Zhang and his former graduate student Linfeng Wan, was formally published in the journal Nature Astronomy on June 2, 2025, officially confirming that Pluto's haze doesn't just decorate its skies, it actively governs the planet's climate. This finding meaningfully changes how planetary scientists think about atmospheric climate control in general. For decades, the standard assumption across planetary science was that gases drive a planet's climate. Carbon dioxide trapping heat on Venus, methane shaping the thick atmosphere of Saturn's moon Titan, and so on. Pluto turns out to be something different. Solid particles, specifically a class of compounds called tholins, are effectively running the climate system instead. Tholins form when ultraviolet sunlight strikes methane molecules high in Pluto's atmosphere, triggering a cascade of chemical reactions that build increasingly complex hydrocarbon compounds. As these particles slowly drift downward through the atmosphere, they build up in layers, forming the haze that both scatters visible light, giving Pluto its subtle bluish glow, and radiates heat away in the infrared, cooling the atmosphere from above in a way that's genuinely unique among the worlds studied so far. The discovery didn't stop with temperature alone either. Webb's data also revealed that methane escaping from Pluto's thin atmosphere is drifting through space and settling onto the surface of Charon, where sunlight then converts it into the reddish organic compounds visible at Charon's poles. In a very real sense, Pluto is slowly depositing material onto its own moon and altering its surface chemistry over time, an interaction researchers say appears to be unique within our solar system. Charon, Pluto's largest moon, is unusually large relative to Pluto itself, roughly half of Pluto's diameter, which is part of why the two are sometimes described as forming a binary system rather than a simple planet and moon pairing. Unlike Pluto, Charon lacks any significant atmosphere of its own, though this newer research suggests it may experience some seasonal outgassing. Its surface is dominated by water ice mixed with ammonia-based compounds, and its most visually striking feature is that large reddish patch at its north pole, informally nicknamed Mordor by the New Horizons science team. It's precisely this reddish coloring that Bertrand's team has now connected directly to methane, escaping from Pluto's atmosphere and settling onto Charon's surface, where solar radiation gradually converts it into the same kind of complex organic tholin compounds responsible for Pluto's own haze. Once this haze-driven cooling mechanism was confirmed at Pluto, researchers naturally began wondering whether similar processes might be happening elsewhere. Zhang has pointed specifically to Saturn's moon Titan and Neptune's moon Triton as worlds that share broadly similar nitrogen and hydrocarbon-rich atmospheres, meaning the same fundamental haze chemistry could plausibly be playing a comparable role there too. Titan, in particular, has actually been studied in far greater detail than Pluto up to this point, thanks to NASA's Cassini spacecraft, which spent 13 years orbiting Saturn and repeatedly studying Titan up close, including landing the European Huygens probe directly on its surface back in 2005. Titan's atmosphere is considerably thicker and more complex than Pluto's, complete with actual liquid methane lakes and rivers on its surface, something Pluto's much thinner atmosphere and colder temperatures don't currently support. But the underlying photochemistry that builds up haze particles in both atmospheres appears to follow genuinely similar chemical pathways, meaning insights from one world can meaningfully inform researchers' understanding of the other, even though Titan and Pluto differ enormously in size, atmospheric thickness, and overall environment. There's also a genuinely compelling connection to Earth's own deep history buried in this discovery. Zhang has pointed out that before oxygen accumulated in Earth's atmosphere roughly 2.4 billion years ago, our own planet's atmosphere was dominated by nitrogen and hydrocarbon compounds, chemically not entirely unlike what we currently observe on Pluto today. Studying how haze particles regulate temperature and chemistry on Pluto right now may end up teaching researchers something genuinely useful about the chemical environment on early Earth, long before life as we know it eventually took hold. It's worth understanding just how difficult this particular measurement actually was, because it highlights how much technical precision this discovery required. Pluto and Charon sit extremely close together relative to Earth's distance from them, and for decades, every previous infrared observation of the pair essentially blended their two separate heat signatures into one combined reading, making it impossible to know how much of any detected signal came specifically from Pluto's atmosphere versus Charon's icy surface. Bertrand has explained plainly that earlier instruments simply couldn't tell which part of the signal belonged to which world. Webb's considerably larger primary mirror and far more sensitive mid-infrared instrument finally provided enough resolving power to cleanly separate the two signals, which is precisely what allowed researchers to isolate Pluto's haze emission and directly test Zhang's original prediction with real precision. Specifically, researchers measured Pluto and Charon across a range of wavelengths between roughly 5 and 27 microns, far beyond what the human eye can perceive, capturing subtle variations in thermal radiation as both worlds rotated. By comparing how that radiation changed over the course of Pluto's roughly 6.4-day rotation period, researchers could map out variations in temperature, thermal inertia, and surface composition across different regions of both worlds, and crucially isolate the specific contribution coming from Pluto's high-altitude haze layer, rather than its surface ice. This kind of long-term, carefully calibrated observation simply wasn't possible during New Horizons' brief 2015 flyby, which prioritized capturing detailed images and surface composition data during its short window of closest approach, rather than sustained thermal monitoring across multiple rotations. The team also confirmed a second, related prediction, this one made by Linfeng Wan, Zhang's former graduate student, regarding how Charon's own brightness should change slightly as it rotates, based on differences in its surface ice and thermal properties. The fact that Webb's new data lined up with both of these independently made predictions, Zhang's haze cooling theory and Wan's separate rotational light curve prediction, gave researchers considerably more confidence that they'd correctly identified the underlying physical mechanism at work, rather than simply finding a coincidental pattern buried in noisy data. It's also worth appreciating just how unusual it is, scientifically speaking, for a specific theoretical prediction to sit unconfirmed for as long as Zhang's did, waiting patiently for exactly the right instrument to come online. Zhang proposed his haze cooling theory in 2017, 4 years before Webb even launched, based purely on reanalyzing existing New Horizons data and running detailed atmospheric models. He effectively had to wait, with no guarantee his idea was even correct, for a telescope that didn't yet exist to eventually get built, launched, and pointed in exactly the right direction to test it. That kind of patient, long-term scientific bet paying off this cleanly is part of why this particular story resonated so strongly within the planetary science community once the team finally published their confirming results. It's genuinely worth being careful and precise about what this discovery does and doesn't mean. This is real, carefully measured, peer-reviewed atmospheric physics and chemistry, not evidence of anything artificial or engineered on or beneath Pluto's surface. The finding is remarkable, specifically because it reveals a genuinely novel, naturally occurring climate mechanism, solid particles, actively regulating an entire planet's temperature and driving material transfer to a neighboring moon, something researchers hadn't confirmed happening anywhere else in the solar system before this work came together. Researchers are also actively exploring whether similar haze-driven cooling mechanisms might extend well beyond Pluto, Titan, and Triton, potentially even applying to certain exoplanets with hydrocarbon-rich atmospheres located in cold, dim outer regions of other star systems. That broader exoplanet connection remains speculative and still being tested rather than confirmed, but Pluto's case gives researchers real, physically grounded evidence that this kind of particle-driven climate control is possible in nature, not merely theoretical. There's also a broader instrument story worth appreciating here, since Webb almost didn't happen the way it eventually did. The telescope's development stretched across roughly 2.5 decades, involved thousands of scientists and engineers across multiple countries, and faced repeated delays and budget overruns before it finally launched on Christmas Day 2021. Unlike Hubble, which orbits relatively close to Earth and has been serviced by astronauts multiple times over the decades, Webb operates roughly 1 million miles from Earth, far too distant for any human repair mission, meaning every one of its instruments had to work correctly the first time, with essentially no margin for hands-on fixes if something went wrong during deployment. The fact that an instrument as sensitive as MIRI could then be pointed at a small, dim, incredibly distant world like Pluto and successfully detect a signal. This feint is a genuine testament to how precisely engineered the entire observatory turned out to be. Looking ahead, researchers are hoping to secure additional observation time with Webb to continue monitoring Pluto's haze and atmosphere over a longer stretch of its 248-year orbit around the Sun. Pluto's atmosphere is known to change somewhat as it moves through different points along that extremely long orbital path, expanding somewhat when it's closer to the Sun and thinning as it moves farther away. Continued monitoring could help researchers understand not just the current snapshot of Pluto's climate, but how this haze-driven cooling system responds and adjusts over much longer timescales, adding an entirely new dimension to our understanding of one of the most distant, and now, thanks to this research, genuinely one of the most scientifically interesting small worlds in our entire solar system. Taken together, this research fundamentally reshapes how scientists think about Pluto specifically, and about small, cold, hazy worlds in general. Pluto isn't simply a frozen, inactive leftover sitting quietly at the edge of our solar system. It's home to a genuinely active, self-regulating atmospheric chemistry system, one where microscopic organic particles are constantly forming, drifting downward, radiating heat into space, and even seeding chemical changes on a neighboring moon millions of miles from the sun. It's a completely different way of maintaining a planetary climate than anything else confirmed elsewhere in our solar system, and it took nearly a decade, one bold theoretical prediction, and one of the most powerful telescopes ever built to finally prove it. It's worth ending on just how much this discovery changes the broader question of what makes a small, distant world worth studying at all. For a long time after its 2006 demotion to dwarf planet status, a decision that remains debated among astronomers and the public alike, Pluto occupied an odd place in public imagination, treated by some as a minor footnote rather than a serious object of ongoing scientific interest. This research pushes firmly against that framing. Pluto turns out to host one of the more genuinely novel climate systems confirmed anywhere in the solar system, a mechanism that took a bold theoretical prediction, nearly a decade of patient waiting, and one of the most advanced telescopes ever built to finally verify. That's a remarkable amount of scientific payoff from a world once dismissed as simply too small and too distant to matter much. If deep dives into real, carefully verified space discoveries like this one are your thing, subscribe now, because there's a lot more genuinely fascinating science coming out of Webb's ongoing observations, and we'll be covering it as it happens. And if this particular finding surprised you the way it clearly surprised the scientists who spent 8 years chasing it down, let me know in the comments, and I'll see you in the next one.